Hi team, welcome to Wiggins Maths. In this video we're going to look at the reverse chain rule. Worth pointing out, as with all integration videos that we're doing, we're aiming to become competent in lots of different techniques so that we can use them more readily. Some people like this, some people not so much. Okay, so firstly, important reminder to not neglect the formula booklet. So we can use the reverse chain rule in a few different ways, but we need to be able to observe particular functions like this. So we should be able to spot if a function is written in this way where the denominator, when differentiated, becomes the numerator. So here is our first example. Here we should hopefully see that when we differentiate this, it becomes this. So like we did that before, when we wanted this in the denominator, we used natural logarithms to help. We will do the same here. So if I were to differentiate that, I would get the exact thing that I wanted. So I now know that the integral of that with respect to x must be ln x cubed plus 5 plus our constant. Now, this isn't technically fully correct at the moment, because if x cubed add 5 was negative, then this would be invalid, right? So what we need to do to combat that is we need to actually think a little bit more carefully about how we write our solution by using a modulus symbol. This means that whenever this is negative, we're going to treat it as positive, therefore not making it undefined. Right. This one again, it's a little trickier to spot this time. However, if you were to differentiate the denominator, you would get something related to that numerator. So again, we are going to try guessing that the function was something like this. And when we differentiate that using the chain rule, we will get which isn't far off. It isn't far off what we want, and now I can make it so I will get the correct coefficient. I need to take 1/5, and then of course add my constant of integration. Notice I've used the modulus symbol here straight away this time. Also worth pointing out that this 1/5 could be written as a power here, or this could be written as the fifth root. There are many different ways of writing this as our final answer. Third one, sec squared x differentiates to make tan x, formula booklet. So I'm going to try so when I differentiate, I will get which is nearly what we wanted. Therefore, I know that the integral of this function with respect to x must be 1/3 ln of 3 sec squared x plus our constant. In essence, for this type, we want to try ln f of x. Okay, and then we can adjust the constant where is appropriate to do so. Second observation is if it's written in this form. Okay, so two functions multiplied together, one is the differential of the other, and we can use a slightly different approach here using the reverse chain rule. So here hopefully we can see x cubed plus 7 will differentiate to give 3x squared, or something related to 3x squared. So just like before, we need to imagine what must I differentiate to get this. Well, it's this to the power of 5. So let's try that to begin with. So using the reverse chain rule, or using the chain rule in this case, we will get 15x squared, x cubed, add 7 to the power of 4. 5 from differentiating this term, and the 3x squared from differentiating this term, multiply them together to give you 15x squared, which is not far off. It's not far off what we want. And now I can just make the coefficients equate. So that's going to be 1/5 of x cubed plus 7 to the power of 5 plus c. Okay, again, it's the second form, it's that second observation. Sine x differentiates to give cosine x, or something related to cosine x. So it's sine squared x at the moment, so what would I differentiate to get sine squared x? Well, it's going to be something to do with sine cubed x. So let's try that to begin with. So when I differentiate that using the chain rule, I am going to get 3, a cos x, and a sine squared x, which is not far off. That means I can then equate the coefficients, and this time I want to take 5/3 of that and then add my constant. Okay, so here we have one that is a little trickier. Which of the two forms is it? If you differentiate this, do you get this? Well, no, we don't. Which means if we're going to use the reverse chain rule on this, we need to rewrite it to begin with. So I'm going to rewrite this like this. Now, 5 plus cot x, differential of that, does give me something that's related to cos x squared x. But if I differentiated the denominator as a whole, it wouldn't give me something like that. So now I'm going to try, and be careful with this, to the power of -2. So when I differentiate this, it will give me 2 cosec squared x, 5 plus cot x to the power of -3, just using the chain rule on this. Therefore, I can say now with confidence that cosec squared x over 5 plus cot x cubed with respect to x must therefore be 1/2 of 5 plus cot x to the power of -2 plus my constant of integration. Okay, so just one final example you'll be pleased to know, and it's a special case. Okay, as calculus becomes more complex, there are often examples that require even further thought. So whenever there is sec or cosec involved, we need to think very, very carefully what happens when we differentiate those terms. If we differentiate sec, it still contains a sec term. So therefore, this time, when we're trying to guess what we need to differentiate, instead of using sec to the power of 4x, we're just going to stay with sec cubed x. And you'll see why in a moment when we differentiate sec cubed x. And that's a little bit trickier, this one, so I'm going to formally show you the chain rule. So let's make sure that we can do this successfully. Differentiation of sec, I don't know it. Luckily for me, it is in the formula book. Set is sec x tan x. Okay, so here it's going to be 3 sec squared x sec x tan x. Now I'm just going to tidy this up ever so slightly. So that is 3 sec cubed x tan x, which is very, very close to what we wanted. So therefore the integral of 7 tan x sec cubed x with respect to x must be 7/3 of sec cubed x plus c. Whew. So once again, just to reiterate, reverse chain rule is one of the many techniques that you can use to integrate complicated functions. You may prefer other methods, that's your call. It's definitely worth having this up your sleeve though. Okay, so if you found this video useful, please subscribe, tell your peers. I'll be aiming to upload new videos each week to ensure that we're as successful as possible. And of course, amateurs call it genius, masters call it practice.